Well, Laura Massini-Haughton, the author of that paper of the University of North Carolina, Andrew of Cambridge, is here. Also with us is Toby Weissman, a reader in theoretical physics at Imperial College London. What effect did it have upon you to realise you may have disproved such a commonly held conviction about the nature of our universe?
It was very nerve-wracking, of course, although not a surprise. The history of black holes versus no black holes goes back to at least as far as Eddington in the 1930s. In 1935, he had this argument with Chandrasekhar, who was about to show that there are black holes, that very massive stars collapse under their own gravity into one point in the center. And that story goes back to, later on, it goes back to Oppenheimer and Wheeler, and then Hawking and Penrose singularity theorem, and here we are now.
Potentially, what are the implications of your conviction?
I would think if these results hold, and the calculation was done under a series of approximations, so more work needs to be done, but if it's correct that there are no singularities and no event horizons, just massive stars, then that's one very major place where quantum mechanics is as important as the Einstein theory of gravity.
And what do you think of these the implications of this calculation?
Well, the implications, if it turns out to be confirmed, would be very dramatic. It would be a real surprise.
A revolution, wouldn't it?
It would be, I think, a revolution in terms of people who think about black holes, certainly. It would be very revolutionary. One of the reasons is that one of the cherished views we have is that when a black hole forms, we don't need to understand quantum mechanics to understand how the horizon, the event horizon, develops. That's the surface out of which you can never escape. So we, up to this point, were fairly convinced that standard Einstein's classical theory, ignoring quantum mechanics, works there. We understand if you went inside the black hole, at some point you have to worry about quantum mechanics at this singularity. But at the horizon we didn't think so, whereas if Laura's paper would claim otherwise.
But you don't believe it, do you?
I have not had long enough to study it. It was in my email inbox this morning, and so, you know, this is a technical work, and I would need to go through the calculations in detail to say...
You'd be surprised if it works?
It's absolutely surprising, given results in the past, but, of course, we're all hoping for a surprise.
Are you worried that it may not be proved by others?
I am worried that once I and a collaborator in Cambridge have dropped the assumptions that were made in this first part of the work, that we will challenge ourselves. But having spent the last 5 months working intensively and focused on this problem alone, I do think that the results will hold up.
How much do you think this sort of discovery, this sort of theory, a black hole? I mean, no one's actually seen a black hole, have they?
Well, no one's fallen into one that we know of. But to say people haven't seen a black hole, I think, is probably wrong. By very definition of a black hole, light can't escape from it.
Yes.
So you will never see a black hole directly, but there have been many indirect observations of black holes.
But we are at the limits here of human ambition and human capacity, aren't we?
I would say to understand astrophysical black holes as they are in our universe, we're not at all at the limits. I mean, observations in the last few decades have made remarkable progress. We now know, for example, at the center of our Milky Way is a black hole that's a few million times the mass of our sun. And we're pretty certain about that fact. Now, what happens when you fall in and quantum mechanics becomes an issue is more complicated. But the existence of these objects...
Okay, so I should probably clarify what you mean. Usually we associate black holes with the existence of a singularity at the very center, known in colloquia as the edge of space-time itself. That translates into it's so exotic that we don't really understand what happens at that point. But there's
Where are
also
the limits?
besides that, the second feature associated with black holes versus massive stars is something known as an event horizon, which is a sort of boundary, not a physical boundary, but a point, a location in the space outside the black hole where not even light can escape. So whenever an object, a star, has a singularity at the center and an event horizon outside, then we would call that a black hole. What my work has showed is that once you include Hawking radiation in the interior of the star collapsing into a black hole, and that is the key point, Hawking radiation is produced by the collapsing star, the one that is about to collapse into a black hole. So once you include that Hawking radiation in the interior of that star will never reach zero size. It will never collapse all the way to a singularity. It will still be a very massive star, the same kind of mass that the black hole would have had. So it will have the same gravitational forces that we normally associate with indirect observations of black holes, but it won't have an event horizon or a singularity.
Rather exciting, isn't it?
It's all very exciting, Jeremy.
Thank you both very much.